Today we are going to go over topic 5.1, using the mean value theorem. So before we introduce the mean value theorem, let's take a look at something called Rolle's theorem. There's Michel Rolle, French mathematician, Michel, from the 1600s. He was one of the most vocal critics of calculus. Later in life, Rolle came to see the usefulness of calculus. So maybe sometime in your life you might find the usefulness of calculus if you don't see it right now. So let's start off with this little activity. Let's place 2 points anywhere on the coordinate plane. 2 points. Okay, let's use A and B as our x values. Okay. Pick any y values that are the same for both x values. So let's pick a y value here and the same y value here. Okay. And now we're just going to connect them with something that's continuous and differentiable. So, continuous and differentiable. Okay, no corners, cusps, or points of vertical tangency. And this is kind of wonky here, but let's fix that a little bit. Okay. So continuous and differentiable everywhere. If it's differentiable, it's continuous. It's implied. Okay, so here's the conclusion that Rolle came up with. There must be at least one point on your function where you can draw a tangent line that is horizontal in between A and B. So there's at least one. At least one. So if a function is continuous and differentiable, and the y values are the same, so this right here, this point here is A, f of A, and this point here is B, f of B. If f of A equals f of B, which it does, then there must be at least one point here, some points somewhere between A and B, we'll call C, that you can draw a tangent line that's horizontal. That's Rolle's theorem. Okay? Let f be a function that's continuous on a closed interval and differentiable on an open interval. Okay, so if a function is differentiable, this is something you'll hear a lot. If a function is differentiable on the closed interval, it is implied that it is continuous. I'm sorry, this is the open interval. I don't know if I said open or closed. If a function is differentiable on an open interval, that means differentiable everywhere between A and B. You can't be differentiable on an endpoint because there's not a left side and a right side. So if it's differentiable everywhere between A and B, then it's continuous on the closed interval AB. Okay? And then we'll get more into open and closed. AP test does not make a big deal about endpoints when it comes to differentiability increasing and decreasing, because many books have different answers about endpoints. So on the AP test, they don't focus a lot on the endpoints when it comes to continuity and differentiability. Okay? So keep that in mind. But if a function is differentiable on an open interval, it is continuous on the closed. Okay, So now Rolle's theorem says if f of a equals f of b, there's at least one number in the interval such that the first derivative is equal to 0. That's Rolle's theorem. And here is the first derivative at c. So f prime of c is equal to 0 because f of a equals f of b. Now, what does that tell us? What is this line here between that goes through f of a and f of b? What is that called? That's called the secant line, right? What's the slope of the secant line? 0. What's the slope of this tangent line? 0. Right? So that is going to lead us into the mean value theorem. Okay? But let's go ahead and illustrate Rolle's theorem one more time. Determine if Rolle's theorem applies on this interval, or on this function between -2 and 2. State thoroughly the reasons why or why not the theorem applies. If the theorem does not apply, or does apply, find the value of c. Okay, so first thing, number 1. Is f of x continuous? So is this a continuous function? Are there any holes? Are there any cusps? Are there any points of vertical tangency? Are there any vertical asymptotes? No, this is just a polynomial. Polynomials are continuous everywhere. So f of x is continuous on the closed interval -2 to 2. That is true. Second thing, is it differentiable on the open interval? Well, just because it's continuous doesn't mean it's differentiable. Okay, so again, I've already talked about points of vertical tangency, cusps, vertical asymptotes. Do we have any of that on a polynomial? Can you take the derivative of this polynomial over this? Yes, you can. So continuity does not imply differentiability, but differentiability implies continuity. So f of x is differentiable on the open interval. Now, it's not differentiable on the closed because of the endpoints. Okay, so does Rolle's theorem apply? Well, we need to test. We need to find f of -2. So -2 to the 4th power minus 2 times -2 to the 2nd power. What does that equal? That's 16 minus what? 8. So f of -2 equals 8. What is the other endpoint equal? Minus 2 times 2 to the 2nd. That's 16 minus 8 again. So another 8. So yes, f of -2 equals f of 2. So we can use, yes, Rolle's theorem. Because these are equal. Rolle's theorem applies. Okay? So let's go ahead and find the derivative of f of x. Now that we know it applies, let's go ahead and see where it happens. So we have 4x cubed minus 4x. Rolle's theorem says that the first derivative will be equal to 0 somewhere at least one point between -2 and 2. Let's see what that point or points would be. So we have 4x times x plus 1 times x minus 1. So there are 3 x values where your first derivative is equal to 0. However, we only want the answers from -2 to 2. So this is 0. Right? This is -1, which is in our interval. Don't give me answers out of the interval. And then 1, which is also in our interval. So there is 1. There's actually 3. Okay? That's where your first derivative is equal to 0. So let's look at the graph. The graph of f of x equals x to the 4th minus 2x squared. Let's sketch a graph of this. F of x is going to be, let's pull out an x squared, and we get x squared minus 2, right? So that's going to give us 0 and plus and minus the square root of 2. Those are our x-intercepts. That's where your y value is equal to 0. So 0, 0, square root of 2. Well, the square root of 2 is greater than the square root of 1. And the square root of -2. I'm just estimating. So those are our zeros. Y-intercept, plug in 0, you get 0. End behavior, both ends go up. Okay, so how can this help us with our sketch? How can this help us with our sketch? Well, we know that this is where your max and your mins are going to be. So right now in 10th grade, we're doing sketch with zeros and end behavior. And I told them in calculus, they'll learn how to figure out what happens in between. So now you can have, remember in 10th grade, you used to just estimate how high and how low it went. Well, now you can actually find how high and how low it goes. So this is the function here. So if you know that your max and mins occur here, find out the y values now. So if I plug in 0, I get 0. So 0, 0 is on the graph. When I plug in a -1, plug in -1. I don't know if we should maybe make a table, but or can we do that in our head? Plug a -1 into here, you get a +1. Plug a -1 into here, you get a +1. So you get 1 minus 2. You get -1. So -1, -1 is one of your max or mins, because it has a slope that's equal to 0. Okay? Now, I'm probably going to move this over a little bit, because the square root of 2 is about 1.7. I think it's somewhere around there. So we need to move it a little bit further away, because otherwise our graph is not going to be very symmetric. So I'm going to move it closer to 2. Okay? So then when I plug in 1, I should get the same thing. When I plug in 1, I get -1. So now you can add more. Again, in 10th grade, we used end behavior and we used zeros. Now, using Rolle's theorem, we can find max and mins. So we know this is how low it goes, because we know that the end behavior is going to go up. We know that this has to be a minimum. It's called a relative minimum. We know this has to be a relative max, relative min. Whoops. I'm going to make it nice and smooth here. Relative max, relative min, and back up again. Okay, and again, that should be a nice smooth curve. Okay, so adding on to 10th grade using Rolle's theorem. First derivative is equal to 0, you should be able to draw tangent lines, horizontal tangent lines. That means that we have a min and a max here. Again, these are called relative mins. This is called a relative max. These are actual absolute mins as well, because an absolute min is the lowest place on the graph. This is not an absolute max because the graph goes on forever. Okay? All right. So, what does the mean value theorem say? Well, let's go through a little exercise on this. Let's visualize what the mean value theorem says. It says if f is continuous on the closed interval, and differentiable on the open interval, then there exists a number c such that the first derivative is equal to f of b minus f of a over b minus a. This we call instantaneous. Rate of change. Instantaneous rate of change. I didn't feel like spelling it because I probably would spell it wrong. Equals, what's this? That's the slope of the secant line. This is the slope of the tangent line. This is the slope of the secant line. We can't use that terminology in calculus. This is called the instantaneous rate of change. What's this called? The average rate of change. That's the mean value theorem. So as long as the function is differentiable and continuous, well, if it's differentiable, it has to be continuous over an open interval, then there exists at least one number, c, such that the instantaneous rate of change equals the average rate of change. So let's take a look. Here again, we have a and we have f of a. Over here, we have b, and the y value is f of b. Okay? Label a segment whose length is f of b minus f of a. F of b, the y value minus the y value. So let's do that in purple or pink. So this right here is our f of b. This right here is our f of a. So we're going to label the line segment from f of b to f of a. F of b, f of a. Those are our y values. Okay. Now we're going to label a segment whose length is b minus a. Okay. So that's going to be this one right here, b minus a. Now, the quotient f of b minus f of a. F of b minus f of a divided by b minus a. Rise over run, right? Rise over run. That's the slope of the secant line. So that quotient is the slope of the segment joining the 2 points, A, f of A, and B, f of B. That's the slope of the secant line. And in calculus, we call it the average rate of change. Okay? Now, f prime of c gives the slope of the tangent line. Now it says that c is somewhere in between a and b. So it gives the slope of the tangent line to the curve at some point c. Its y value would be f of c. So can you estimate where the tangent line would be the same or equal to this slope of the secant line? Do you see? Again, that's an estimate. Those slopes look the same or close, right? That's the mean value theorem. There's at least one point, C. There's at least one x value C in that interval where the slope of the tangent line equals the slope of the secant line. But we call it the instantaneous rate of change equals the average rate of change. Okay? Or the velocity equals the average velocity. Okay? The two lines drawn on the graph of f of x are parallel to each other. That's why their slopes are equal. And then this is the conclusion of the mean value theorem. So let's go ahead and restate it. Okay, there are two parallel lines, one through a point A, f of A, and B, f of B. Okay, that's the secant line. And the other is tangent to the curve at a point in between. We call it C, f of C. That's the mean value theorem. So, determine if the mean value theorem applies to this function. State the reasons why. All right, so let's go through our reasons. Number one, the function must be continuous on the closed interval. Well, here's a sketch of the graph, a piece of it. Now this is a rational function. It has a different branch, but we only care about 1 to 5. So when you plug in a 1, you get -2. So we only care about from here to 5. So when you plug in 5, you get 3 minus 1, which is 2. So we're going from that interval, okay, from 1 to 5. Is the function continuous? Yes. So number one, f of x is continuous. Let me help if I can spell. Continuous on the closed interval 1 to 5. Okay. Is it differentiable? Yes. No cusps, corners, points of vertical tangency? So 2. F of x is differentiable on the open interval from 1 to 5. Again, can't be differentiable because we're only talking about an interval from 1 to 5. All right. Now, we don't have to see that the y values are the same. That's Rolle's theorem. What we have to do is we have to find the instantaneous rate of change. The instantaneous rate of change, which is our first derivative. The first derivative is 0, and then we're going to use the reciprocal rule. So that's the opposite of the derivative of the bottom all over the bottom squared. So that's our instantaneous rate of change. And our average rate of change, our f of 5 minus our f of 1 over 5 minus 1, that's equal to what? F of 5, we said, was 2, minus a -2. So our average rate of change is 4/4, which is equal to 1. So the slope of the secant line, again, we call that the average, we call that the average rate of change, has a slope of 1. Okay, somewhere in between there, we're going to have a C value where the instantaneous rate of change is equal to the average rate of change. So let's take our instantaneous rate of change on the interval and set it equal to our average rate of change and solve. So x equals plus and minus the square root of 5. Now again, the answer is just the square root of 5. That's the C value because we only want from 1 to 5. So let's go to the square root of 5. The square root of 5 is bigger than the square root of 4. Okay, so let's see, what is the square root of 5? This isn't going to come out to be very, very nice. Square root of 5. Oh, let me get my calculator here. Square root of 5. Have I got a bad picture? Oh. Oh, okay. It's a square. All right. I was saying that's not going to be right. I was thinking it was 4. No, the square root of 4. So it's just a little bit bigger than 2. It's actually 2.2. So it's somewhere right around here. It's the square root of 5. No wonder. I was going to put it up here, and I'm like, that's not right, because those wouldn't be parallel. So there's your C value. And you have just proven, using the mean value theorem, that if I draw a tangent line at that point, and again, this is just an estimate, but if I draw a tangent line at that point, they will be parallel to each other. So the mean value theorem doesn't say that the tangent line will be parallel to the secant line. I mean, yes, it does, but you wouldn't say that. The calculus definition is the average rate of change is equal. There's a point where the instantaneous rate of change at a point, in this case, C equals the square root of 5, is equal to the average rate of change over an interval. So the instantaneous rate of change is at that point. The average rate of change is over an interval. So make sure you keep those two things straight. Okay? All right. So you are going to do these equations or these problems here. Okay? You are going to find the equation of the tangent line to the point. So here you have the point and you have the slope. They want you to actually not just find the C value, but they want you to find the equation of the tangent line. Okay? So you have to go a little bit further. Here you're going to tell me why the mean value does or does not apply to these graphs over this interval. So start with the first two. Is f of x continuous on the closed interval, and is it differentiable everywhere on the open interval? Okay, so if the mean value doesn't apply, tell me why, and then answer a story problem. If you watch this wonderful video, if you click on it, it might give you a hint. All right, so that's mean value theorem.